Okay, great. Thanks for the invitation. Yeah, it's really great to be back here. Yeah, today's talk is going to be about both symplectic geometry and combinatorics. So this is a symplectic geometry seminar, so I'm going to start with a little bit of combinatorics. Okay. So the combinatorics that we're going to be discussing involves polytopes. So I want to think about a polytope d-dimensional. So some d-dimensional polytope in R to the n. Okay. And, well, there's a much studied object associated with such a polytope called its Ehrhart function. So to a polytope like this, I want to associate a function. This is a counting function. So what it is it counts points in, well, the polytope scaled by p, and it counts integer lattice points in this polytope. And this is called the Ehrhart function of p. It's normally studied for t a positive integer. Okay, so for almost all this talk, I'm going to be studying two-dimensional polytopes in R2. So that's probably what you should have in mind. And anyways, I just count lattice points in various scalings of this polytope. So this is a much-studied combinatorial object. You might wonder why. Well, it has very many nice properties. So the basic structure theorem of such an object is as follows. So the the classical observation, which is due to Ehrhart from the 1960s, something like this, is that if I take an integral polytope, then this counting function LP of t is actually a polynomial in t. That's right, yeah. That means that the vertices are all at integer lattice points. Right, so if I take an integral polytope, then this counting function is actually a polynomial in t. And, well, its degree is the dimension of the polytope. Okay, and some of its coefficients are of interest. So some coefficients of interest. So for example, the coefficient of the leading order term is the area of the polytope. So for example, the coefficient of the leading order term is the area, so the volume of the polytope. Okay, which is cool because, for example, it means that if I have an integral polytope, I can compute its volume just by counting some lattice points. Okay, which is sort of neat. Yeah, you should think of this as a higher dimensional generalization of Pick's theorem, right? So Pick's theorem gives you a way to do this in dimension 2, but evidently we can recover the volume of a polytope in any dimension by doing enough lattice point counts. Yeah, that's right. Okay, so this is sort of the basic result due to Ehrhart, but there's some other cool properties. So there's some other nice properties. No, you don't need it to be full dimensional. Yeah, you can take a d-dimensional. In this talk, it is going to be full dimensional, but you don't need it to be full dimensional. Yeah. Okay. So this has some other nice properties. For example, this is a polynomial. So this counting function, it really only makes sense for positive integer t, but it's a polynomial in t, where this is a polynomial. So I can evaluate it at negative integers. Okay, so I can evaluate p, I can evaluate this polynomial at some negative integer. I'd like to know what that is. Well, it turns out that that counts lattice points in the interior of the polygon. Okay. So this is called the reciprocity theorem. Yeah, sorry. Thanks. Right. So this P naught, this is the interior of my polytope.
Oh,
So the interior. Right, sorry. Of P. Yeah, please stop me if you have any questions, especially about issues of handwriting and things like this.
We're just symplectic geometers and not combinatorics.
Right, no, exactly. Yeah, that's why you should especially stop me. Yeah, yeah.
It's a little thing, it's a with a polynomial and the polytope denoted by the same P.
Ah.
No, it's a big P.
Yeah, that's interesting. Okay, sure, I'll call it Q of T to avoid. Yeah, just you wait until you have triangles floating around too.
And is it Q of negative T?
Yeah, then it would be Q of negative T. Exactly, thanks. Right.
So it's always positive, this number?
Yeah, that's right. For example, if I take this and I evaluate it as a negative number. Oh, no, sorry. That's definitely not right. There's another factor, which is that I want a -1 to the d to get this to work. OK, but then it actually does work, right? So where d is the dimension, remember, d is the dimension of my polytope. Yeah. Right. But anyways, we're going to be mostly talking about the case where everything is dimension 2. Okay, so then that is positive. Okay, and there's other sort of, so these are sort of the classical, theorems of Ehrhart theory, but there's sort of other theorems that are mostly due to Richard Stanley, called, for example, the monotonicity theorem. There's sort of a monotonicity theorem. Etc. Okay, but these aren't so interesting for our talk. So that's the basic story.
Can you give us like an example?
Yeah, I'll give an example in a second, but I want to finish with the basic story, and then I'll give an example. Well, I might as well give an example. So sort of the fundamental example is, say I have a triangle that looks like this. So this is sort of the simplest possible polytope. OK. Then, so I'm going to call this capital T, which is going to get me into some problems. But anyways, so, well, maybe I'll just call this P to have it agree with everything else. So again, what's the Ehrhart function of this? I want to consider all scalings of this, and I want to count the lattice points. And you can just check that, again, I only need to do this for positive integer t. And this comes out to be equal to 1/2 t squared. Remember, the coefficient of the highest order term is the area, which is 1/2 here, plus 3/2 t plus 1. OK. So, if you've so you can do this in many ways. But anyways, this is sort of a simple example of what these Ehrhart look like and how you should maybe be imagining polytopes like that. OK.
How do you figure out the 3/2 and 1?
You cheated to get 1/2.
How do I figure out what the coefficients of this are? Yeah. So you can do this by direct computation, for example. It's sort of a combinatorial calculation that's not especially hard, but maybe not that interesting. So to do this, you would want to know how many lattice points there are in the triangle with vertices 0t, t0, and 0, 0. And then you just want to know how many non-negative linear combinations of 1 and 1 are t. You can just compute that combinatorially. Of course, the cool thing, though, is if you believe the main theorem of Ehrhart theory, to compute a polynomial like this, you just have to count the number of lattice points in this triangle and then the triangle scaled by 2. And then actually, so for example, we see here that the coefficient of the constant term is 1, which we would expect because if we scale this down by 0, which isn't quite allowed by how I define it, but that's sort of another property of these functions, I get exactly 1 lattice point. So once you know it's a polynomial, you just have to do a few counts, and then you can figure out what it is.
Okay.
Yeah. OK. So yeah, great. All right, so that's the basic structure theory in the integral case. So now the next generalization was due to various people, I don't know, 20 years later, which is what happens when the triangle is rational, when the polytope is rational. OK. So now I want to imagine that my polytope has vertices on the rational numbers. Okay, and I want to know how much of this theory goes through. So, well, the basic structure theory says that now this counting function, rather than being a polynomial in T, it's what's called a quasi-polynomial in T. Okay, so what does that mean? That means that it's a polynomial in T, but with periodic coefficients. Okay, so for example, well, just to give you an example of a quasi-polynomial, I could have something that looks like Q of T, and, well, it's going to be a bunch of polynomials determined by the congruence class of T mod some integer. So, for example, it could be equal to, T squared. I'm going to call it Q of X because my T's seem to be confusing people, especially with the plus signs. So it could be, say, X squared plus X plus 1 if X is congruent to 0 mod 2. Okay, and then I'm allowed to have different coefficients if X has a different equivalence class. So it could be 3x squared plus X plus 1 if X is congruent to 1 mod 2. Okay. So that would be what a quasi-polynomial looks like. Okay.
Although the leading term has to be the same.
Yeah, the leading term, well, this is just supposed to be an example of a quasi-polynomial, not necessarily a quasi-polynomial that comes from an Ehrhart function. But indeed, if this came from an Ehrhart function, the leading term would have to be the area. Yeah. Okay, so that's the basic structure in the rational case. And the sort of main theorems still hold, at least versions still hold from the integral case. For example, if I take this quasi-polynomial and I evaluate it at negative values of x, I get the number of lattice points in the interior of the polytope. Okay, and there are also interesting things you can say about the period of this quasi-polynomial. I mean, here I'm doing things mod 2. You can bound the period of these periodic coefficients in terms of the geometry of the polytope, which is also nice, but sort of not so relevant for this talk. So, since we have to absorb a lot, maybe just focus on what a quasi-polynomial is. Okay, so the main theorems, anyways, from the integral case still hold in the rational case. So are there any questions about this? I know, that the combinatorics are a little new, so let me know if I'm going too fast or too slowly. Okay, so that's the rational case. But now the interesting thing is that the irrational case is actually closely connected to symplectic geometry, and even more interestingly, doesn't seem to have been studied at all. Okay, so what happens in the irrational case? So at least to Richard Stanley and I, this seems to be not studied at all. So not studied. Okay.
And this means just at least one vertex coordinate as a coordinate, that's irrational.
Right, yeah. It just means not rational. But that's a really good question, because that sort of gets to part of the reason why this hasn't been studied. I mean, surely it's the case that if you assume nothing about the polytope, sort of nothing interesting. I mean, maybe there's something, but certainly like the main structure theorems of Ehrhart theory don't hold. But the game here is maybe there are some conditions that I can apply to some of the vertices where I get a reasonable Ehrhart theory.
So like, just look at an ellipsoid, we make the like A and B in a triangle like rationally independent.
Yeah, that's right. That's the idea. Right. So the cool thing is that a combinatorialist looks at that and sees a triangle, whereas a symplectic geometer, at least one with embedding interest, sees a symplectic ellipsoid. And it's sort of helpful to view that as a symplectic ellipsoid. Yeah, that's sort of exactly right. Yeah, that's exactly right. OK, cool. So soon enough, I'll tell you what we know about the irrational case. There's a lot that we'd like to know, but we do know some interesting things about the irrational case. But I want to switch gears and go to symplectic geometry to tell you a little bit about how the irrational case comes up. OK, unless there are any questions about this. OK. So Joe gave me a very nice lead-in. We want to talk about now symplectic embedding problems. Okay. And there's a lot that one can say here, but I guess what I want you to take out of this is why irrational Ehrhart theory sort of comes up naturally here. Okay. And that'll also be relevant. Remember, we're going from symplectic geometry to combinatorics and back. And this is sort of relevant when we want to go back. OK. So what's the basic problem in symplectic embedding problems? I have two symplectic manifolds. And I want to know, when does there exist a smooth embedding of one into the other that pulls back the symplectic form on the target to the symplectic form on the domain? Okay. So this is a symplectic embedding. And, well, determining when these exist can be very subtle. Especially when the dimension of the domain and the target are equal. Okay, when the target has much higher dimension than the domain, there's a version of Gromov's H principle, which often makes this very topological. But especially when the dimensions are equal, this is closely connected to questions about moduli spaces of holomorphic curves. Okay. So one example of just how subtle this can be, even for simple examples of the same dimension, is due to McDuff and Schlenk. Now, I've sort of mentioned this before, so most of you presumably have seen this, but I will try to go through it quickly. OK, so what did McDuff and Schlenk do? Well, they studied embeddings of symplectic ellipsoids. OK, so these are sets OK, they're open subsets, the way I've defined them, of R4. And the symplectic form here is given by restricting the standard symplectic form on R4. OK, and what McDuff and Schlenk did is they computed the function C of A, which is equal to the minimum lambda, such that the ellipsoid E1A can be embedded symplectically into the four-ball of size lambda. OK, for non-negative A. OK, so let me.
So what is the normalization? So this, the E form would be.
Right.
Is that the cross-sectional area?
Yeah, it's just an ellipsoid with parameters C, C. OK, yeah. All right. So like I said, some of you have seen this before, some have not. So I'm going to defer to those who have not and say just a few words about how you want to think about this. OK, so the idea behind this function is that if I compute it for a greater than or equal to 1, it completely determines when I can embed a four-dimensional ellipsoid symplectically into a four-dimensional ball. OK, you only have to compute it for a greater than or equal to 1 because of symmetry properties of this ellipsoid. Okay, so I fix some a like 2, and I want to know what's the smallest ball I can put it in. Okay, and the game here is that this function, it's always greater than or equal to the square root of a, because symplectic embeddings are volume preserving. Okay, but the deviation of this from the square root of a is related to what obstructions are truly of a symplectic nature rather than volume preserving nature. So in particular, it's related again to questions about moduli spaces of holomorphic curves. Anyways, so what is this function c of a? Well, so we should first put the volume constraint. So this is the volume constraint, square root of a. And we just want to know what happens for a greater than or equal to 1. So at 1, it starts at 1. And then what happens is it goes linearly. Okay, so it goes by some line here. And if you were to extend this line, it would go through the origin, which is sort of interesting, but not super important for this talk. And it goes this way until a equals 2. All right, so if you're familiar with Gromov non-squeezing, this is roughly what you would expect from Gromov non-squeezing, because it's saying at 2, it's saying that the optimal embedding of an E12 into a 4 ball is into a ball of size 2, which is the embedding that one gets by inclusion. Okay, so this is an expression of very strong rigidity. The optimal embedding here is given by inclusion. But then at 2, it veers to the right, and it goes straight to the right, straight until it hits at 4. Okay, so in contrast to when the ellipsoid is stretched by a factor of 2, when the ellipsoid is stretched by a factor of 4, all the symplectic obstructions vanish, and we're just left with the volume-preserving obstruction. Okay, so an ellipsoid that's 4 times as wide as it is tall fully fills a ball of size 2. So then what does it do? Well, it has to stay above this, so it has to do something. So it repeats the same general pattern. It goes via a line through the origin for a while, and then it veers to the right. And then it does it again, and it does it again, and it does it again and again and again and again, okay, until it limits on this value. So what is this value? This value is the golden mean to the 4th. Okay, so here tau is the golden mean. Right. So the function is rather rich up until the golden mean to the 4th, which in particular is an irrational number. Okay. So this irrational number is sort of sitting at the origins of irrational Ehrhart theory. Okay. So this is an irrational number. Okay, so now these numbers, well, the numbers 2, 4, these are themselves rather interesting. The ones that we care about are where these steps hit the volume curve. So these a values are themselves very interesting. So if I have a piece like this here, okay, then the coordinates here, this whole piece is determined by the odd index Fibonacci numbers. So this coordinate here is a ratio of consecutive odd index Fibonacci numbers. Okay, so these GNs, these are the odd index Fibonacci numbers. Okay, and because of this, this whole thing is called the, quote, Fibonacci staircase. Now, that's really the only part of McDuff and Schlenk's result which is relevant to our talk. But just for fun, I'll point out roughly how the rest of it works. So this golden mean to the 4th, this is about 6.8. Okay, it turns out that at 17 over 6 squared, the function, it's just equal exactly to the volume obstruction forever after that. So if my ellipsoid is stretched enough, then all obstructions vanish except for the volume obstruction. And then in between these two sort of phases, the function is mostly like this, but there's a few intervals where it rebels. So it sort of is mostly the volume except for 18 intervals on which it's not. Okay. So this is the only part that we're interested in, but the result is nice, so it's good to get it right. Okay. So are there any questions about the result of McDuff and Schlenk? Right. So I apologize if you've seen this before. I think the rest should be new, and maybe some of the combinatorics is also new. Okay. And yeah, so again, the teaser here is that the fact that this is an irrational number is related to the irrational Ehrhart theory that's coming. But yeah, please stop me if you have any questions or handwriting issues or whatever. OK, so, well, McDuff and Schlenk's result is very nice, but but the question is, what does this have to do with Ehrhart theory? OK, and more generally, actually, McDuff and Schlenk's, I think it's fair to say, really doesn't have anything to do with Ehrhart theory. I mean, this is a kind of long and hard argument. It uses equivalence between Seiberg-Witten and Gromov invariants and lots of combinatorial calculations about continued fractions. So this is sort of a long and hard argument. And it's not clear that this has anything to do with Ehrhart theory. So a natural question is, where is the Ehrhart theory here? Well, the Ehrhart theory comes from a theory for obstructing four-dimensional embeddings called the theory of embedded contact homology capacities. Okay, so it turns out that not just for embeddings of ellipsoids, but for embeddings of four manifolds in general. So for four-dimensional embeddings, there's a tool called embedded contact topology capacities. There's a tool called embedded contact homology. Okay. That can be used to study these things. So more precisely, what ECH, so these are called ECH capacities. What ECH capacities allow you to do is, given a symplectic four-manifold M omega, ECH capacities allow you to assign numbers ck of M omega. Actually, I'm going to write this way. Numbers so they're monotonically increasing. They're also possibly infinite, with the property that if I can embed one symplectic manifold into another, then I get that the kth ECH capacity of M1 omega 1 is less than or equal to the kth ECH capacity of M2 omega 2 for all k. Okay. So these ECH capacities, they obstruct symplectic embeddings. So they obstruct symplectic embeddings. Okay. So again, this probably is familiar to most of you. This is sort of how how symplectic capacities always work. But it's worth getting this right just to make sure we're all on the same page. Okay, and I'll say a few more words about ECH in a moment, but I want to make sure everybody knows what the idea is. So using this ECH capacity package, I take a symplectic four manifold, I get this sequence of non-negative real numbers, and they have the property that if I can embed one four manifold into another, then the fifth one has to be less than or equal to the fifth one. And so I can use this to study symplectic embeddings, in particular to obstruct symplectic embeddings, because in a lot of cases I can compute them. And maybe the fifth one is bigger for M1 than for M2, which means I can't embed M1 into M2. Okay, so that's sort of how this story works. All right, so the embedded contact homology here means that they're defined using a very interesting variant of symplectic field theory called embedded contact homology, which really is just defined for contact 3 manifolds. Okay. So are there any questions about this? So like I said, we can compute them for ellipsoids. And so now the idea is to take the result of McDuff and Schlenk, which after all is a full computation of when an ellipsoid embeds into a ball, and see what it says about ellipsoids. Okay, sorry, I'm going to block this off here. So for ellipsoids, you can just compute these ECH capacities. It's not even hard to compute, really. I'm going to call this property star here. Okay, so this property, I'm labeling it star for future reference. And what the computation for ellipsoids gives you, so what you get so what you get is that if I have one ellipsoid that embeds into another, then, well, if I form the following sequence of integers, I'll tell you what this is in a second. Sorry. If I have one ellipsoid that embeds into another, then that gives me an inequality of sequences of integers. Where this NAB sequence, this is the sequence whose kth term is the kth smallest entry in the matrix MA plus NB, where M and N are non-negative integers. Okay, so if I can embed one ellipsoid into another, then I get an inequality of sequences like this, where by this inequality I mean term by term inequality. Okay, so again, how does this sequence work? In a moment I'll give you an example, but what I'm saying is I just take all non-negative integer multiples of A and B and I list them in order, and then that's how it works. So for example, if I want to know what the sequence N1, 2 looks like, well, then I get a 0, because the smallest non-negative integer linear combination of this is where the coefficients are 0. Then I get a 1, because I get 1 times this. I get a 2, but I actually get 2 2s because I can have a 2 times this, et cetera, et cetera. Okay, 2 3s, okay, 3 4s, et cetera. Okay, so what the theory of embedded contact homology capacities gives you is that whenever I have an ellipsoid embedding like this, I get an inequality of combinatorial sequences. Okay. So are there any questions about this? give you a second to catch up. I know I'm going at a, well, maybe a fast pace, depending on how much you've seen this before. I think I don't want to do that, but I'll do that during the question and answer, just because I still have sort of a lot more ground to cover. I guess I'll say briefly that embedded contact homology, it's a variant of symplectic field theory, and it really just pays attention to what's going on at the boundary. So this ellipsoid, even though it's open, it has an implied boundary here, which is some contact 3 manifold. And what happens is that the embedded contact homology, it has various classes. And the embedded contact homology capacities are defined by looking at the minimum symplectic action required to represent the various classes in embedded contact homology. So what will happen is the embedded contact homology of this is actually a graded thing. And it's only supported in non-negative even grading. So the first ECH capacity is the minimum action required to represent the class in ECH in degree 2. And the second one is the minimum action required to represent the class in degree 4. Okay. So they're defined pretty simply in terms of embedded. OK, great. So you don't even have to ask in the question and answers. I guess what I wanted to avoid was writing something on the board. Okay. Yeah, so are there more questions about that? OK. So anyways, we got this sequence. And this is sort of non-obvious. I mean, if you sort of read McDuff and Schlenk's proof, it's sort of not clear why you would get this, but you do. Well, this is starting to look like counting lattice points in a triangle, but we should spell this out. Okay, so how do we think of these sequences? There's kind of several ways to think of them. But anyways, they connect to Ehrhart functions. Because, well, the number of terms in the sequence NAB that are less than or equal to some number t Okay, so if I take this sequence and I want to count the number of terms that are less than or equal to, let's fix some positive real number t. So I'm fixing some positive real number, capital T. Then, well, the number of terms in this sequence that are less than or equal to t this is well, it's the number of lattice points in the triangle which has slant edge xa, so ax plus by is less than or equal to t. Okay, so in other words, if I fix some positive real number t here, I get a triangle like this. And I'm saying this line is the line. So actually, if this is the edge, then it's equality here. OK, so if I want to study these sequences, I end up studying these triangles. Okay, and I end up counting lattice points in these triangles. So this is the basic connection between this sequence and counting lattice points in triangles. OK, so by using this together with the computation of McDuff and Schlenk, you learn some interesting things about counting lattice points in triangles. So by combining all this, with the result of McDuff and Schlenk gives some interesting facts about counting lattice points. Okay, so for example, okay, so if we just study what's going on at these odd index Fibonacci number points, we get, okay, well, I'm going to write it over here. So actually, I think this is sort of an important enough point that I'm going to redo it over here. Okay, so for example, if we apply this whole story to certain points on the graph, we get that the number of lattice points in this triangle, okay, so I'm going to write the triangle like this. So I have two different triangles here. I'm going to call this PN, okay, and I'm going to call this one. So this triangle has vertices that look like this. Okay. And I'm going to make this some Pn of L. Okay, so this L is just some auxiliary number. So I have these two triangles. Okay, and I'm going to call this P of L. Okay, so what I get, if I apply McDuff-Schlenk, gives that the number of lattice points in this triangle on the left is always greater than or equal to the number of lattice points of this triangle on the right. Okay. So I'll make sure everybody understands the statement of that. And then I'll try to unwind that for you.
Are these G's the Fibonacci units?
Yes, these G's are exactly the odd index Fibonacci numbers. So remember the GNs are the odd index Fibonacci numbers. Okay, so what I'm saying here, so these are consecutive odd index Fibonacci numbers. So the way you want to think about this, so you get this for any L, but actually it's only an interesting statement if L is a non-negative integer. Okay, so this is only interesting when L is a non-negative integer. So what I'm saying is that you have these two different families of triangles, and by applying McDuff and Schlenk's result about symplectic embeddings of ellipsoids together with the theory of ECH capacities, you get some non-obvious inequality of lattice points in the first relative to the second. Okay, and we can rephrase this in terms of Ehrhart polynomials. Okay, so if you rephrase this in the language of Ehrhart polynomials, you get that the Ehrhart polynomial for this triangle Pn, okay, I guess the way I've defined it would be Pn of 1, but sort of fairly stupid, okay, is bounded from below by the Ehrhart polynomial of this other triangle. Okay, so you get some inequality of of Ehrhart polynomials, and the question now is why. Okay, so let me call this double star, and Aaron Kleinman and I were interested in why this is true. So why is double star true? Okay, so just to emphasize what I'm saying by this, this is a purely combinatorial fact. This is just a fact about counting lattice points in certain triangles determined by the odd index Fibonacci numbers. So technically speaking, if you follow this argument, it's rather convoluted. I mean, you want to use Taub's equivalence between Seiberg-Witten and Gromov invariants to get a symplectic embedding of ellipsoids, and then use the theory of embedded contact homology capacities to determine some fact about counting lattice points in triangles. And what Kleinman and I were interested in is surely there's a more direct way to do this. I mean, I guess somehow you could imagine, it'd be very strange if there was some other planet where people were doing were doing mathematics, and they were interested in counting lattice points in triangles and trying to prove this, and you sort of flew to the planet and told them you need to develop the theory of symplectic embeddings of ellipsoids to answer this question. They would be sort of very surprised. So this kind of doesn't seem right. So there should be a purely combinatorial explanation for this. Okay. And actually, the purely combinatorial explanation is quite interesting, and that's sort of the genesis of the irrational Ehrhart theory.
Counting. I mean, you could kind of twist it around and say, let's have a more exotic lattice and think in terms of, a sort of standard polytope triangle or something like that. And you might imagine, it seems like these Ehrhart functions are saying things about the lattice.
Sure.
Okay. So is there any reason to expect, though, that, is there any kind of general thing? They're not identical. But is there anything that can you generalize this to lattices? Do you expect any kind of weird inequalities like that for special kinds of sequences of points for more general lattices?
Yeah, I think it's a very good question. So there's two questions, right? There's sort of a question of, are there combinatorial things that you can say here, and are they related to symplectic geometry? I think surely, so you can do Ehrhart theory more generally. As you say, you can take a lattice in R to the n, rather than the integer lattice. And then you can, instead of looking at integral polytopes, you can look at polytopes, with vertices on lattice points for that lattice. And surely there's sort of statements like this that hold there. At least I would say surely. Who am I, though? But I don't know if they have any significance for symplectic geometry. But I think it's an interesting question.
They're very, there are these things where you're interested in, as you expand fundamental regions, and you grab anytime a new lattice point jumps in. That sequence of lengths is important for solving short vector problems.
Yeah.
And you get these increasing sequences of real numbers that matter a lot to the structure of the lattice.
Sure. Yeah, I should say also that that sort of reminds me of these kind of, the kind of things that you're talking about also come up a lot in Rabe dynamics. That's sort of how I got interested in this, is that similar ideas come up in dynamics. But maybe we can defer that to the question and answer, because I have a few more things that I want to say in the remaining time. But anyways, I think those are very good questions. OK, so I want to say what the point is anyways. So we wanted to understand why this was true. And now the nice thing is, if you try to understand combinatorially why this is true, you learn something stronger. So we tried to prove this, and it was quite hard, actually, until we realized that you could prove that these Ehrhart polynomials are actually equal. OK, so we showed that they're actually always the same.
At what point did you guys try to do that?
I don't know. I think we'd had, a couple beers or something, and we sort of felt like, well, I think, in truth, we sort of computed a bunch of examples, and they were always the same, and then we realized that would be a lot easier to show. OK, so we showed that these Ehrhart polynomials are actually equal. Okay. So what does this have to do with irrational Ehrhart theory? Well, I'll remind you that this triangle Pn okay, so again, this triangle, this length parameter over here is gn plus 1 over gn, and this parameter over here is gn over gn plus 1. Okay, and what I'm saying is that for any n, the Ehrhart polynomial of this triangle is equal to the Ehrhart polynomial, the standard Ehrhart polynomial. Okay, so I have, this standard triangle. Okay, so for any n, these two triangles have the same Ehrhart polynomial. So in particular, if I take the limit as n goes to infinity, then these two triangles still have the same Ehrhart polynomial. Okay. So this implies if I take the limit as n goes to infinity, then this triangle, which I'm going to call p twiddle, okay, so this has vertices now tau squared 1 over tau squared. So this implies that the Ehrhart polynomial, I'm going to call this p twiddle. This implies that the Ehrhart polynomial of p twiddle is equal to the Ehrhart polynomial of what I called p of 1. Okay. So I should say this slightly differently. This implies that the Ehrhart function of p twiddle is equal to the Ehrhart function of p of 1. In particular, this triangle, the Ehrhart function of p twiddle is a polynomial. So in particular, the Ehrhart function of p twiddle is a polynomial.
Can that be seen directly, or is that possible?
Yeah, no. So that was sort of the beginning of my work with Li and Stanley, was exactly that question. We wanted to try to see that directly. And indeed it can, actually. Yeah. But sort of, like I said, this was sort of nothing had been known about the irrational case, and it seems that nothing had been known because no one had guessed that the Ehrhart function of such a thing might be a polynomial. Okay, so this is sort of maybe the most important point of the talk. So you want to make sure you understand this. Yeah.
Can I check I understand the reasoning here? So I thought what the McDuff-Schlenk graph showed was that the ellipsoid on the left embedded into the ball on the right.
Yeah, that's right. But then it gets reversed when you want to count the number of terms. So that's exactly right. The ellipsoid embeds into the ball. Okay, so then that says that the NAB sequence of the thing on the left is less, of the ellipsoid is less than or equal to the NAB sequence of the ball. But then when you then figure out what that's saying by counting the number of terms less than a particular value, that reverses the inequality.
So the point is that this would be the same for any ellipsoid that lay above that staircase.
Yeah. Well, no. So anytime you have, no, that would be the same for anything that lies above that staircase. Yeah, that's right. Yeah, that's right. Yeah, that's also right. Okay. So anyways, so this thing is actually a polynomial. And this gets back to Lisa's question. So this is an example of an irrational polytope whose Ehrhart function is a polynomial. And what's the point here? Well, one of the vertices actually is an integer, but the other two, well, the interesting thing is these are quadratic irrational numbers. Maybe that's the thing to take away from this, that there might be some version of this that holds when the vertices are quadratic irrational numbers instead of just rational numbers. Okay. So what we wanted to know, so with Li and Stanley, we wanted to know, well, more generally, if I study, see, there's another reason for studying this if you're a combinatorist. If you're a symplectic geometer, this is a symplectic ellipsoid or maybe a weighted projective space or something, at least one of those or whatever. But if you're a combinatorialist, these are also natural things to study because if you have a polytope, you can triangulate it. So the sort of triangles, if you read Ehrhart's proofs, or at least how they've been sort of modernized. I don't actually know how Ehrhart did them. Usually they start by taking some sort of triangulation of the polytope and studying triangles. Okay, so these are sort of like the elementary building blocks of polytopes anyways. So what we wanted to know is what's special about the golden mean here. In other words, if I take a triangle with vertices, u0 and 0v, okay, where u over v is irrational, we wanted to know, so I'm going to call this T uv. Okay. So we wanted to know when is the Ehrhart function of this thing a polynomial and when is it a quasi-polynomial? When is it a polynomial? So like I said, one expects that if I just take random irrational numbers, it probably shouldn't be anything. Okay, but the hope is that in more cases than the golden mean, this has some interesting structure. Okay, and it turns out that the sort of most beautiful answer, I think, is to when it's a quasi-polynomial. So what we found is that the Ehrhart function, so we found that the Ehrhart function of this thing is a quasi-polynomial so I'm going to put the word primitive in here, which I'll explain in a second. But anyways, it's sort of a not an essential point. So it's a primitive quasi-polynomial if and only if. So the question is, what conditions do we want on u and v? And well, so what it turns out is that you want both u plus v and 1 over u plus 1 over v to be integers. Okay, so where alpha and beta are positive integers. So what I'm saying is if you have a triangle like this and you want to know when its Ehrhart function is a quasi-polynomial, you take your irrational numbers, u and v, and you see whether u and v satisfy this equation. So it might be worth, a good way to think about this is, well, these equations, so let me again, so let me call this a system of equations triple star. So triple star implies, so if you think about this for a few minutes, you learn that triple star implies that u and v are quadratic irrationalities, but not all quadratic irrationals work. It's just like 3 plus root 2 or something. So it's an element of the integers when I adjoin a solution of a quadratic equation. Okay, so if you like, it's something of the form a plus b root c over d, where a, b, c, and d are all rational numbers. Okay, so this implies that u and v are quadratic irrationals. Right. Okay. But not all quadratic irrationals satisfy this. So not all. Well, so I guess I'm going to say that there's certain quadratic irrationalities. Okay. So the point is that the golden mean, well, it was a quadratic irrational, but if you take the golden mean and you take 1 over the golden mean and plug it into this, alpha and beta here, they both come out to be 3, for example. Okay, so not all quadratic irrationals satisfy this, and some do. Okay, so I'm almost out of time, so I want to say a few more words about sort of what the combinatorially interesting stuff here is and what the symplectically interesting things are. Okay, so first to say something about combinatorics, well, so the hope now is to try to understand more generally what irrational Ehrhart theory would look like, at least in dimension 2. Okay, so as I said, these are like building blocks for two-dimensional polytopes, and you'd like to know if I put a polytope, what kind of conditions do I need on the vertices to have some Ehrhart theory? I mean, it's possible that these are the only examples, but there might be some other interesting examples. I should say, by the way, remember I said that with Ehrhart theory, it's not just that the counting function is a quasi-polynomial. It satisfies some nice properties like reciprocity. We also show that these triangles satisfy all these properties. Okay, so it really is sort of reasonable, at least versions of these properties. There really is a kind of Ehrhart theory for this kind of thing. Okay. As for the symplectic geometry, well, it turns out that, so that I actually will sort of write one or two things on the board. So for the symplectic outlook, so there's sort of one thing which seems very promising. So this irrational Ehrhart theory gives insight into other embedding questions. Okay, and this is the work with Holm, Mandini, and Pires that was mentioned in the abstract. I should also say that Anarita Pires, she's going to give a talk here, I think, about this kind of stuff. So if you're interested in this, she'll sort of be saying much more about this. But the idea of what we're working on in our joint work is, again, this Fibonacci staircase is a rather interesting thing. So we want to know how frequently does something like the Fibonacci staircase occur. So in particular, what we're looking at is we're looking at embeddings of an ellipsoid into a closed symplectic toric manifold. And we want to know when does that have an infinite staircase. And it turns out that this story predicts that there are exactly 12 examples where there should be a infinite staircase. And all the other examples, you expect that the graph, that the embedding function is given by the volume except finitely many intervals where it's linear. That's sort of related to the irrational Ehrhart theory, and Anarita will spell that out more. So more speculative, but there should be some connections to dynamics. So, for example, when you want to count classes in embedded contact homology that are less than a given action, you also end up counting lattice points in triangles. But the non-degeneracy of the contact form usually translates into the triangle being irrational. And so I can sort of later show some examples. But for example, a basic question that one likes to understand in the dynamical world is showing that various manifolds have at least a certain number of Rabe orbits. And a better understanding of how these lattice point counts work could be related to this. And I can show you some examples later. So I think I'll stop there.